Hello again, statistics students. This is Emigh, and this video is on our discussion of section 7.1, estimating a population proportion. Let's start with an example from the Pew Research Center. They did a poll of 1,007 randomly selected adults, showed that 856 of them, which is about 85% of those who responded, know what Twitter is, and that would mean the other 15% do not know what Twitter is. They want us to construct a confidence interval for the proportion of adults that know what Twitter is. They would like us to use a confidence level of 95% and round to the nearest thousands. Okay, first thing I would like to talk to you about is this fancy term, the confidence interval. It can sound a little intimidating in that fashion, but I want you to know that you already know what a confidence interval is. You've used them in your own life. You just didn't know they were called confidence intervals in statistics classes. So let me give you a really basic example of a confidence interval. If you've ever said to your friend, hey, I'll be there at 8 o'clock tonight. Well, give or take 10 minutes because I've got some stuff to do. You have created what's called a confidence interval. You have said you're going to be there, arrival time, somewhere between 7:50 and 8:10. This right here, that 8 o'clock, that's right in the middle of 7:50 and 8:10. It's what's called your best guess or your best point estimate. This give or take 10 minutes thing that you said, that's your margin of error. We're going to use a capital E for margin of error. So if you start to feel overwhelmed with this confidence interval discussion, just try to think of this simple example. Know that you've dealt with these before and that you can get through this. Okay, we first need to make sure that we have a simple random sample, a fixed number of trials, independent trials. Everything can be categorized into two outcomes. They know what Twitter is, they don't know what Twitter is. And our probability of success remains constant, which we have 85%. So our requirements are met. That allows us to run a program called the 1-prop-z interval. So it's going to create the confidence interval for us. So if you take out your TI and you hit stat, followed by tests, you can find tests by arrowing to the right twice. I'm doing this with you here. So stat test. Now we need to arrow down and we want to find the program that's appropriate. Well, we have been asked to construct a confidence interval. So we want to choose a program that ends in the INT for interval. It's really nice how they named it that to help us select the right program. The number 1 in front is because we're dealing with one population opposed to like two populations. The PROP is because we're dealing with a question about proportions, or some of us like to think of it as percents. And Z is because we're talking a normal distribution of data. Okay, so find that program 1-prop-z interval. And when you open it up, it requires 3 different inputs, X, N, and the CL level. X would be our 856, that's our number of successes. Lowercase n would be our 1007. And our C level is our confidence level of 95%. I type that in as 0.95. I don't know if your calculator will accept it as a percent or not, but I do mine as a decimal. There. Okay, and when we run that, it gives us, on the very first line of output, it gives us our confidence interval inside parentheses. And that is called interval notation. But it is exactly the same as this notation here, which is a compound inequality. So I'll talk to you about the multiple ways to write your confidence interval. The first one being what you have on your calculator right there, separated by a comma. So it'll be the lower limit, comma, and then it'll give you the upper limit. And mine goes to the 4th decimal place, and then it'll close parentheses. So that's called interval notation, if you remember that from your intermediate algebra class. This right here is called a compound inequality, and you may also see it as 0.85 plus or minus some margin of error, which we don't have that margin of error right now, but I'll show you in a moment the formula to find that margin of error. All 3 different notations to say the same thing. Now, regardless of those notations, if we want to interpret these results, so translate it back into English, if you will, you want to be real specific about the way you word it. Here's a good example. We would want to word it as, we are 95% confident that the limits of 0.828 and 0.872 contain the true population proportion of adults who know what Twitter is. Okay, I like to display this slide because we get so reliant on the technology, it's easy to forget how impressive the technology is. So this slide right here just walks us through what the technology is doing for us when we run that one prop Z interval. So it's taking our center, our best guess, our best point estimate, and it's adding and subtracting a margin of error to p hat to create a lower confidence limit and an upper confidence limit. So if you're ever asked, well, what's your best guess? Like, don't give me an interval, give me your best guess. That'll be worded as the best point estimate, and you can find that by doing x over n. So in our problem, that was 850, I think it was 6 over 1007, and that would give us back our 85%. So that would have been our best guess of the percentage of people who know what Twitter is. The margin of error, that's the amount that's added and subtracted to and from the p hat to create the lower and upper confidence limits. This is the formula that the program 1 prop Z interval implements. This right here is a z-score. P hat is our 0.85. Q hat is the complement of 0.85, so 0.15. And lowercase n is the 1007, and square roots that whole thing before multiplying it by that z sub alpha over 2 z-score. Then it takes that margin of error and it adds and subtracts it to and from p hat, and that's how we obtain our limits. And I was rambling about the different notations earlier, but here they are spelled out a little bit nicer than how I wrote them in red. Here it is in interval notation, and the same thing expressed right here as a compound inequality. All right, let's do these examples together. 33 randomly selected people were asked if they rented or owned their own homes. 15 said that they rented. Find the best point estimate of the proportion of homeowners. All right, I first want you to catch that it asks for the proportion of homeowners, but it gave us the number of rented. So it's really tempting to go, oh, it's 15 out of 33, but it's actually 15 out of 33 that rent. But then they ask us for the number of homeowners. So it would be 18 homeowners. So it would be 18 out of, let me erase that. There we go. It would be 18 out of 33 homeowners. Now they didn't ask us to round to like the nearest tenth, so we would want to give them the answer, an exact answer, so we'd have to leave it as a fraction, but that fraction does reduce to 6 over 11. Number 2, n is 171, x is 124. Construct a confidence interval with a 95% degree of confidence for the population proportion p. Okay. It says construct a confidence interval, so we're going to want to run a program that ends in int for interval. It's going to be about proportions because we have a number of successes over the total number possible, so we're talking proportions here. And so that will be that program, same one we just used, 1 prop Z interval. So hit stat, test, arrow down to 1 prop Z interval. Go ahead and pause this video and try to input your X, your N, your CL level, and then write your confidence interval below. Okay, welcome back. If you had an output of 0.658 and 0.792, nice job, you ran that program correctly. Number 3 says we have 334 college students randomly surveyed. 103 of them own a car. Find a 99% confidence interval for the true proportion of all students who own a car, accurate to 3 decimal places. Okay, again, I want you to pause this video. I want you to try and run one prop Z interval program, entering your X, your N. Don't forget to make an adjustment to your C level this time, and then write your output accurate to 3 decimal places. Okay, welcome back. If you ran stat test one prop Z interval correctly, then that output in that first line, it should have been 0.243 and 0.373. Okay, in this example, we're given a confidence interval and we're asked to find the best point estimate and margin of error used to construct that interval. Okay, and hopefully that interval looks familiar to you. It's the one about the 85% of adults who know what Twitter is. So if we wanted to find the best point estimate, that would be the number right in between 0.828 and 0.872. We can do so using this formula here, upper confidence limit plus lower confidence limit, and then divide that by 2. And if we do that accurately, we'll get 0.85. If we're asked, well, what was the margin of error that was used in that confidence interval? We would want to find the number right in between those 2 limits, and then the distance from that number to each of the limit, using this formula here, upper confidence limit minus, this time, lower confidence limit, and then divide that result by 2. And if we do that accurately, it turns out that the margin of error used in that problem was 0.022. Okay, let's try this example together because there is a little twist to it at the beginning that I want to point out to you. It says that we have 1,487 adults, showed that 43% of respondents have Facebook profiles. Okay, part A wants us to find a 90% confidence interval estimate of the population proportion. That means we need to find the program that ends in INT because they're asking us to set up a confidence interval. We know it's going to be about proportions, so it should have the word prop in the name. And we only have that one program so far, so we're going to run one prop Z interval. Okay, so go ahead and hit stat, test, and arrow down to one prop Z interval. Okay, once you get there, it's going to ask you for the first input, which is X. That's the number of successes. Okay, well, they didn't hand us X. They didn't say exact X equals this value. Instead, they said 43% of 1,487. Well, that would mean that X is equal to 639.41. But if you type 639.41 into the one prop Z interval program, you're going to get an error back. So what I want you to do is round to the nearest whole number, which would be 639. So use that as your X. Your N would be 1,487. Your C level is 90%, so make sure to adjust that. And then go ahead and run one prop Z interval. And your output should be 0.409 and 0.451. Okay, part B wants us to find the margin of error that was used to construct this confidence interval. And we just learned the formula for that on, just go one slide back if you need to. It is the upper confidence limit minus the lower confidence limit, and you divide that result by 2. And so if you do that correctly, you should get 0.021. Okay, last thing, C. Can we conclude that fewer than 50% of adults have Facebook profiles? Write a brief statement that accurately describes the results. Okay, so we've done the number crunching, but now we need to translate this back into English. So what I think is helpful sometimes is to take these values and look at them as percentages. It just is easier to wrap your head around it, mostly because we learn percentages first. So what we're saying by stating that as our confidence interval, we're saying that we believe the true number of adults who have Facebook profiles is somewhere between 40.9% and 45.1%. So if we feel, they're asking us if we feel comfortable saying that fewer than 50% of adults have Facebook profiles. 40.9% and 45.1% are both below 50%. So I would say with 90% confidence, it does appear that fewer than 50% of adults have Facebook profiles because the interval is completely below 0.50. Okay, the next thing Chapter 7 covers is sample size. So when you're thinking Chapter 7 material, I want you to think confidence intervals and sample size. That's all about Chapter 7. Confidence intervals and sample size. Okay, so if you're asked how many sample items must be obtained, they're asking you to tell them the necessary sample size. If you have an unbiased source and their data on the topic that you're also researching that includes an estimate of p hat, then you can use this equation here to find your sample size. And when you see lowercase n equals, you should always think, oh, okay, that's the sample size formula. All right, so this formula is dependent on four things: z sub alpha over 2, so that's a z-score, p hat, q hat, so you'll get p hat from your unbiased sources data, and a margin of error. Well, let's say that you do not have an unbiased sources data or estimate of p hat, then you can't use the formula above because it's dependent on p hat. So instead we'll use this formula here, which is dependent on a z-score called z sub alpha over 2 and a margin of error. So you can see that the p hat product of p hat and q hat is replaced with the 0.25. It's kind of interesting that if you think about it, if you didn't have a different source's estimate of p hat, then you would have no choice but to go, okay, it's 50-50. Well, if your p hat was 50.50, that would mean q hat would also have to be 0.50. And the product of 0.5 and 0.5 is 0.25. So that's where that 0.25 comes from. If you're thinking, where in the world did they get that random 0.25 from? That's where. Okay, so I think you guys should feel pretty comfortable coming up with q hat, should you need to. Its complement, q hat. Your margin of error should be given to you. But what about this z sub alpha over 2? Well, we've had practice finding z-scores. We can do so by running inverse norm, but we haven't really talked about a z sub alpha over 2. So the next slide has one purpose. It looks like a pretty overwhelming slide, but the next slide has one purpose, and it is to help us find this z sub alpha over 2, which is necessary for sample size as well as some other formulas in the future. Okay, so I'm going to walk you through 3 different examples showing how to find z sub alpha over 2. All right, first one. It wants us to use a confidence level of 90%. They want that to be the area in green. And just a note that if you're not given a confidence level, 95% is the default that you should use. Okay, if you have a 90% confidence level, then you have a alpha of 0.10. Easiest way to think of this would be, okay, if I'm talking 90%, that means I'm leaving behind 10%. And so 10% as a decimal is 0.10. That's where that comes from. And then we're going to run our inverse norm, and we need to know the area to the left of z sub alpha over 2, so we can run inverse norm. And I'm telling you, if your confidence level is 90%, then your output, your z sub alpha over 2, will always be 1.645. Let me elaborate by using this graph right here. Okay, the 90% goes in the middle, the green area, as a decimal. The 0.10 or alpha has to get cut into two parts. So you take the 0.10, you divide it by 2, and that's where we get the 0.05 from. You see 0.05 in this tail and 0.05 in this tail. So we're going to run inverse norm, and the area to the left of this z sub alpha over 2 is not 0.9, but 0.9 with an additional tail of 0.05. That would be an area to the left of 0.95. Let me just write that down for you. The area to the left of the z-score we are interested in is 0.90 plus another 0.05, therefore giving us 0.95. All right, so I want you to take out your calculator. I want you to go second distribution, inverse norm, and use your area to the left as 0.95. And if you run that correctly, you'll get an output of positive 1.645. Now the other tail is also cut off, and that is going to be the negative 1.645. It is not a coincidence that it's the positive and the negative. It always will be, because these graphs are symmetric about the vertical axis. Okay, that may have seemed a little overwhelming. I'm going to erase all this red stuff, and we're going to do it again. Here we go. This time they want us to use a confidence level of 95%. So I'm going to put the 95 in the center of the graph right there. That leaves us with 5% left. So we've got to take that 5%, change it to a decimal. That's how we get the 0.05. But we have to split that 0.05. Half of it can go in this tail, and half of it has to go in that tail. Half of 0.05 is 0.025. Okay, now you'll take out your calculator, you'll run inverse norm, and you need the area to the left of z sub alpha over 2. Well, the area to the left, it's very tempting to just put 0.95, but remember you have 0.95 plus one of the red tails. So your area to the left needs to be 0.95 plus another 0.025, giving us an area to the left of 0.975. So I want you to run inverse norm, area to the left 0.975, and if you run that correctly, you will get an output of 1.96, and the negative 1.96 is the negative z sub alpha over 2. Okay, I want you to pause this video. I'm going to erase all the clutter one more time. Pause the video, and I want you to try and take these numbers, 99%, this somehow, and this somehow, and I want you to label all three on this graph right here. Okay, pause the video now and try to label that graph. Okay, welcome back. If you labeled that graph correctly, you put 0.99 in the middle. You put half of 0.01 in each tail, which would be 0.005. You put a positive 2.576 there and a negative 2.576 there. You need to know how to do this. If they change this up on us and say, tell us an 80%, using 80% level of confidence, then figure out the sample size, then you need to know how to construct this with 80%. But I will tell you that these three are the most popular. You're going to see these three the most in your homework questions. And it's nice and necessary to be able to construct this from scratch, but it's also nice and saves some time if you can go, okay, they said to be 90% confident, so my Z sub alpha over 2 is 1.645. They said to be 95% confident, so my Z sub alpha over 2 is 1.96. And if they say to be 99% confident, then my Z sub alpha over 2 is 2.576. Let me show you what I mean. Companies are interested in the percentage of adults who buy clothing online. How many adults must be surveyed to have a 99% confidence level that the sample percentage is within error by no more than 3 percentage points? Part A wants us to use recent results from the Census Bureau that 66% of adults buy clothing online. Okay, a lot of information already, can be very overwhelming. How do you even start? Well, sometimes you need to just back away from the question and all the detailed information and just figure out what they're asking you to do. And the answer is right here. How many? They're asking you to find N equals question mark. They're asking you to find the sample size of something. They give you a confidence level of 99%. They give you a margin of error of 3 percentage points, but we never enter 3% in our equations. We would use a margin of error 0.03. And part A is saying you've got someone else's data. You've got a p hat of 0.66. So the formula you should use is this one. Lowercase n is dependent on a z-score, p hat times q hat, and your margin of error. Okay, what is your first necessary input? That z sub alpha over 2. And the way you find it is based on the 99% confidence level. I'm going to go back one slide and figure out my z sub alpha over 2 by finding the line that starts with 99%. Erase all this other stuff. Okay, so this is the line that we're interested in. This line tells us that 99% level of confidence. We need to use z sub alpha over 2 equals 2.575. P hat we know is 0.66. Q hat would be the complement of that, which would be 0.34. And our margin of error would be 0.03. Pause this video and try to type that into your calculator. Welcome back. If you type that in correctly, you should have got 1654.520129. And with sample size, we always round up to the nearest integer. And we don't always round up because you're always supposed to round up. We always round up in sample size questions because the definition of the sample size is the minimum number you have to sample. So if you ever round down, even though that may seem like the right thing to do because you're following the regular rounding rules, then you have not talked to the minimum necessary. So basically, in sample size questions, always round up. Interpretation of that would be to be 99% confident that our sample percentage is within 3 percentage points of the true percentage. A simple random sample of 1,655 adults is needed. All right, let's try part B. Assume that we have no prior information suggesting, like we did before, the p hat being 0.66. In that case, we would need to use this formula here, which is dependent on two things, z sub alpha over 2 and your margin of error. And we know that ZSubalpha over 2 is dependent on the confidence level, 0.99, leading us to 2.576, and our margin of error is given to us as 3 percentage points, which we would use in an equation as 0.03. Pause this video and try to type that in your calculator. Welcome back, and if you type that in correctly, you should have got 1,843.27111, which, tempting to round down, because regular rounding rules would say to do so, but we always want to round up for sample size. So 1,844, interpretation of that result is for you right there. Okay, if you understood those two examples for sample size, then you should be able to get yourself through this question right here. How many adults need to be surveyed in A and B if we have a different confidence level of 90%? So pause this video and try to redo parts A and B, except change your confidence level to 90%. Okay, welcome back. And part A, the only adjustment made would be from the 2.576, it would change to 1.645. And that is because ZSubalpha over 2 is dependent on the confidence level. So here your confidence level was 99%, leading you to 2.576. And here your confidence level is 90%, leading you to 1.645. And that would equal 675. Part B, using that 1.645 for ZSubalpha over 2, typing that in carefully would lead you to 752. If you got those right, good job. If not, practice them again, and you should be able to get yourself through these sample size questions rather easily. They are straightforward, but they do require some practice. Oh, and that finishes our discussion on section 7.1. Thank you for joining me. My name is Emigh, and I will see you next time.